Okay, this is going to be my modeling of a neuron and how it receives a stimulus and turns that into an action potential and then transmits it to the next cell. So I have before you this neuron on paper that you can't see all at one time. So, oh, here, this will be handy. This is the neuron cell body or soma. These represents the dendrites. This would be the axon. Okay, this is the axon. And then down on this end, we have the axon terminals. So these are the telodendria and the synaptic bulbs. Okay, so I am going to set up the neuron, the resting membrane potential of the neuron. So at rest, the neuron has a slightly negative charge on the inside and a slightly positive charge on the outside. And it has more potassium on the inside and just a little potassium on the outside, and then more sodium on the outside and a little sodium on the inside. So that would be the resting membrane potential of the neuron. And if you measure this, it measures at a negative 70 millivolts is a resting membrane potential. So just resting membrane potential negative 70. So hopefully you can see that it's the purple is negative, the green is positive, and then more potassium inside and more sodium outside. Okay, so now what I'm going to place in here are some membrane proteins that are found in the neuron membrane, and I'm really concerned only about the membrane proteins in the axon and in the synaptic bulbs. Okay, so I'm just placing them down in this pattern that I created. Not that they're arranged like this, but just for our purposes, we're arranging them like this. Okay, and of course these membrane proteins would be all the way around, but we can't picture them all the way around. We're just doing two-dimensional. And then I'm going to arrange the synaptic bulb. So down here I have some different channels. And then around out here I have calcium. And then these represent synaptic vesicles. And this NT represents a neurotransmitter. Okay. So we'll talk more about that when we get to that part. So we're going to go back to the cell body and the dendrites, because the first thing that's going to happen is there has to be a stimulus that creates a graded potential. So it depends on what neuron you're looking at. So this is a multipolar neuron. So this would be either an interneuron or a motor neuron. If it was a unipolar neuron, then it could be a sensory neuron. So a stimulus creates what are called graded potentials. And a potential is just the charge across the membrane, the potential energy stored in the membrane from the electrical charge, from the difference in charges. And graded potentials are different amounts. Okay, so the resting membrane potential, remember, is negative 70. In order to create an action potential, we need to reach a threshold value of negative 55 millivolts. Okay, and that threshold value will sum in this area called the axon hillock, where the cell body and the neuron meet. Okay, so these white cards are going to represent different graded potential amounts. Okay, and these are created by the stimulus. So the first graded potential is negative 5 millivolts. So I was at negative 70, now I'm at negative 75. Okay, so then I have the next graded potential is plus 10 millivolts. Okay, so I went from negative 75 to negative 65, but I still need more. So my next graded potential is negative 5 millivolts. So now I'm back where I started at negative 70. Okay, and then my next graded potential is plus 15 millivolts. And so that actually gets me to the threshold potential of negative 55 millivolts. Okay, so those graded potentials have to sum or add up to the threshold potential of negative 55, and they did. So now this is when our action potential is going to start. So what happens is once we reach that threshold value, that causes these voltage-gated sodium channels to open. So this is a voltage-gated sodium channel, and it opens up because of the charge that was reaching the threshold. And then sodium will rush in. Okay, when that happens, the membrane is depolarized, and so that causes the inside to be positive compared to the outside. So when we're depolarizing the membrane, we're making it more positive, and sodium channels opening are what make it more positive. Okay, so then this depolarization causes the next sodium voltage-gated sodium channel to open. So this voltage-gated sodium channel opens, sodium rushes in, that depolarizes the membrane, so our charges switch. Okay? And we just repeat this process. So this sodium channel opening, this depolarization causes the next depolarization to happen. So the voltage-gated sodium channel opens, sodium rushes in, the membrane depolarizes. Okay, so when I say the membrane depolarizes, I'm making the inside positive and the outside negative. And then our last voltage-gated sodium channel is opening. This is just the last in our simulation. More sodium rushes in. I depolarize this section of the membrane. I'm going to go ahead and depolarize this section of the membrane too. Okay, now behind that, almost simultaneously, but actually a little bit slower. Okay, we're going back to the beginning. This voltage-gated channel is just going to temporarily open, and then it closes, and then this potassium channel, voltage-gated potassium channel opens, potassium moves out, and then potassium is going to repolarize the membrane, and that means it's going to make the inside negative compared to the outside. Okay, so we have this channel, the sodium channel closes, the potassium channel opens. Okay, potassium moves out, and I repolarize the membrane, make it more negative by switching the charges. Okay, so sodium channel closes, potassium channel opens, potassium rushes out. I repolarize this side of the membrane, switch the charges. And that brings us to our last. Our sodium voltage beta channel opens, our potassium channel, or that closes, our potassium channel opens, potassium exits, and I repolarize the membrane. Okay, so if we look, we can now see that it's negative on the inside again and positive on the outside, like when we started. Okay, and then all these potassium channels close. They take a long time. They're slow closers compared to the sodium. Sodium channels open and close fast. Potassium channels open and close slowly. So we've restored our charges in the fact that we have negative charges on slightly negative on the inside and slightly positive on the outside. But if you look at our resting membrane potential, we had sodium on the outside and potassium on the inside. And we no longer have that. Now we have a bunch of sodium inside and a bunch of potassium outside. So we have in our membrane these blue sodium-potassium pumps, and it's their job. We have another one down here. It's their job that they're going to pump sodium out and potassium in. Okay. And in reality, they pump 3 sodiums out and 2 potassiums in. But we're not counting. We're just pumping sodium out and potassium in. Oh, well, we pumped out one too many. Okay. So now the sodium potassium pump has restored our ion concentration. Okay. So now we're going to move down to the transmissive segment. Okay. So what happens here is this would have depolarized also. The depolarization here would open voltage-gated calcium channels. Okay, all these calcium channels open. And then calcium rushes in and binds to this synaptic vesicle. Okay, the binding of the synaptic vesicle then causes the synaptic vesicle to fuse with the plasma membrane of the synaptic bulb and release the neurotransmitter. So again, the binding of calcium causes the synaptic vesicle to move, fuse with the membrane of the synaptic bulb and release the neurotransmitter. So fuse, release neurotransmitter. And now our neurotransmitter is in the synaptic cleft, and it would bind to receptors on the next cell, on the effector cell. And the effector could be another neuron, or it could be a muscle cell, or it could be a gland. And we studied what happened already if the effector was a muscle cell. That neurotransmitter would have been acetylcholine, and it would have bound to receptors on the muscle fiber. Okay. If it was another neuron, it would just be binding to receptors on the dendrites. That's like what we did at the beginning, and it would be creating a new stimulus. Now, what has to happen here is that the neurotransmitter should not stay in the gap, because if it stays here, then it's continuously stimulating the next muscle, and we don't want it to continue stimulating the next cell. We don't want it to be continually stimulated, so we have to have a way to get rid of it. So it can be broken down. Acetylcholine, that's what happens to it. Acetylcholinesterase is in this synaptic cleft, and it breaks down the neurotransmitter. Or the whole thing can just be retaken back up into the synaptic bulb. Okay, or even the parts can be retaken back up into the synaptic bulb, and then the neurotransmitter is put back together and bound in synaptic vesicles again. So we keep reusing these same neurotransmitters is ultimately what happens. Okay, so that's my down and dirty modeling of the action potential.